So, I am going to solve a numerical on air refrigeration cycle. This is your video lecture. A dense air refrigeration system of 10 TR capacity works between 4 bar and 16 bar pressure. The air leaves the cold chamber at 0 degree centigrade and discharges air at 25 degree centigrade to expansion a cylinder after air cooling. The expansion and compression cylinders are double acting. The mechanical efficiency of compressor and expander 85 and 80% respectively. The compressor speed is 250 rpm and has a stroke length of 250 mm. First COP, second power required, and third bore of compressor and expansion cylinder. Assuming isentropic compressor and expansion as polytropic, n is equal to 1.25. Now what are the given things? Q is equal to 10 TR, P1 is equal to P4 is equal to 4 bar, P2 is equal to P3 is equal to 16 bar, T1 is equal to 0 degree centigrade, that is 273 K, T3 25 degree centigrade, that is 25 plus 273 298 K, efficiency of turbine 80 and RPM of the compressor 250 RPM, length stroke 250 mm, and N polytropic process 1.25. Now we will draw the PV diagram and TS diagram. PV diagram: 1 to 2 isentropic compression, 2 to 3 condensation, 3 to 4 expansion in the expansion turbine, and that is polytropic process. PV raised to power n is equal to constant, and 4 to 1 in that is in the cabin temperature, that is cooling effect. It is shown on the TS diagram as well. 1 to 2 isentropic compression, 2 to 3 condensation, 3 to 4 expansion in the expansion turbine, and 4 to 1 cooling in the cabin. So T2 temperature of the air at the end of the isentropic compression in the compressor. T4 temperature of the air at the end of polytropic compression in the turbine. Now treating as an ideal gas, T2 upon T1 is equal to P2 upon P1, gamma minus 1 upon gamma. P2 P1 is known, 16 by 4, gamma 1.4. So T2 is equal to T1 into, you calculate it, 1.486. T2 is equal to T1 into 1.486. T1 is known, 273 into 1.486 is equal to 407 K. Similarly, for the expansion in polytropic process, T3 upon T4 is equal to P3 upon P4 n minus 1 upon n, because it is polytropic process. It is given n is equal to, value of n is given 1.25. Putting all those values, 16 upon 4 pressure ratio, that will give you 1.32. Similarly, T4 will be equal to T3 upon 1.32, and that will give you 298 upon 1.32, 225.7 K. In that way, T2 and T4 are calculated. Now we have to calculate the COP. We know that the work done by the compressor during the isentropic process 1-2 per kg of air, that is given by WC compressor work W12, gamma upon gamma minus 1 into R, T2 minus T1, 1 upon efficiency of the compressor. Putting all those values, 1.4 upon 1 minus 1.4 minus 1, R value is standard, that is given 0.287, that is the difference in temperature, 405.7 minus 273 into 1 upon efficiency 0.85. Calculating all those values, we get 156.8 kilojoule per kg. Taking R is the standard value, 0.287 kilojoule per kg K. Now work done by the expander in the process 3-4, that is WE expander, that is 3-4 n upon n minus 1 into R, T3 minus T4, and multiplied by the efficiency of the expander. Putting all those value, n value it is already given, 1.25 upon 1.25 minus 1 into R 0.287 into change in temperature 298 minus 2 to 5.7 multiplied by efficiency 0.8. It gives you 83 kilojoule per kg. That is your work done by the expander. So minus W expander, and that is 150. We have already calculated 156.8 minus 83, that gives 73.8 kilojoule per kg. Now we know the heat absorbed during the constant pressure process 4.1, that is cooling effect per kg of the air. Refrigerating effect produced will be QA, refrigerating Cp, change in temperature T1 minus T4, because T1 minus T4 is the cooling effect. Cp already we know, T1 T4 already we know, so we have calculated 47.3 kilojoule per kg. That is your work done. So COP, heat absorbed upon work done, QA upon W 47.3, 73.8, 0.641 answer. Next, power required. Now 20 TR capacity is given, so 20 into 10 TR capacity is given, 10 into 210, 2100 kilojoule per kg, and refrigerating effect already we have calculated, 47.3 above we have calculated, refrigerating effect, that is cooling effect. So mass will be 2100 upon 47.3, that will give 44.4 kg per minute. Then work done per minute, that will be MA into W. W already we have calculated, mass we have just calculated. So the work done per minute 3277 kg per minute, and power required 3277 divided by 60, that will give you in kilowatt, kilojoule per kg, kilojoule per second, that will be kilowatt, 56.6. Next, the last one, bore of the compressor of the expansion turbine. Suppose D is the expander, V1 volume compressor, VD, V4 that is expander. So P1 V1 is equal to MARA T1. So V1 can be calculated from here. V1 will be MARA T1 upon P1, 44.4, 287 R standard, 273, 4 into 10 power 5, 10 power 5 because we have changed the bar into Newton per meter square. So Newton per meter square, so 10 power 5 से नीचे multiply किया, that will give 8.7 meter cube per minute. Now V1 is equal to pi by 4 d square, L is the length, stroke length 2 into 2 because double acting cylinder is there, and is the RPM. So V1 already we have calculated from here, 8.7 pi by 4 d square into 0.25 into 2 into RPM, that will give 98.2 d square. So from here we can calculate the d, that is the diameter, that is 0.2976 or 297.6 millimeter. Then for the expander, we know that V4 upon T4 is equal to V1 upon T1, ideal gas equation. V4 we can calculate, then V1 T4 upon T1 already we know the value, so it is coming 7.2 meter cube per minute. So V4 is equal to calculated, V4 is equal to pi by 4 small d square, that is the expander length into 2 times into n. Putting all those values, 7.2 into pi by 4 d square into 0.25 into 2 into 250, that is 98.2 d square. Now this d square is equal to 7.2 divided by 98.2, and that gives 0.271 meter equal to. So all the values have been calculated. First we have calculated COP, then power required, then we have calculated bore of the compressor and expander cylinder. That's all.